Okay, let's see how this goes here. Okay, we're gonna look at some of these examples. You guys have to help me out because I don't have my glasses here. So the first question is gonna be, we have to find the limit as x goes to infinity. And we have what? 2x squared plus x minus 3, everything over, is that 3x squared? Okay. Minus 2x plus 1. All right, remember, based on what we've done so far, right, what do you guys always want to do here when you have a rational function? Do you guys remember? Yeah, always divide by the highest power for your variable in your denominator, right? So in this case, it's going to be that x squared here. So we're going to divide every term by x squared here. So you're going to get now the limit x goes to infinity, 2 plus 1 over x minus that 3 over what? X squared. You're going to divide by 3 minus 2 over x plus 1 over x squared. Okay, could you guys see that? Okay, so remember there's some cancellation going on here for you. Right, x squared goes away, you got cancellation. This is going to be 1 over x. Cancellation with your x squareds. This is 1 over x, and you got plus 1 over x squared. Now I'm going to say, again, you're going to use those properties. So you get to use properties of limits now. So by properties of limits, I'll go through all the properties again for you so you guys can see that, and then after that we won't. So if those people weren't here, you got the limit now, 3 minus 2 over x plus 1 over x squared. That's the limit of a quotient, which is quotient of limits, right? And then limit of sums and differences, or sums and difference of limits. So we can say the limit of 2 plus the limit of 1 over x minus that limit of 3 over x squared over the limit of 3 minus the limit of 2 over x plus the limit of 1 over x squared. Okay, and then again, what do you guys remember you can do? Pull out your what? Constants, right? So we're going to write it as here the limit of 2 plus your limit of 1 over x minus 3, limit of 1 over x squared, limit of 3 minus your 2, limit 1 over x, plus the limit now 1 over x squared. Okay, so now we're going to go through this here. We're going to find those limit values, right? What's the limit of a constant again? 2. What's this limit? Remember, these are limits as x goes to infinity, so we should remember that, and I'll put that here. This is as x gets big, okay? Positive. So this limit's going to be what? 0. This limit is 0. This is the limit of a constant again. You got limit of 0, and this is 0. So altogether here, we're going to have 2 plus 0 minus 3 times 0 over 3 minus 2 times 0 plus 0. So when we do the arithmetic, what do we end up with? This is going to be 2 over 3. And that value is what? Right? We've been saying that value is finite, right? So if it's a finite value, what do we just find here? Remember? Y equals 2/3 is a horizontal what? Asymptote. All right, there you guys go. So that's the first example. All right, now we're going to go to the next one here. We have the limit now as x goes to minus infinity, x squared plus 3x over 5 minus x. So again, we're going to divide by what? Yeah, the highest what? The highest power for the variable in your denominator. In this case, it's going to be an x, right? So here's what you get. The limit, x goes to minus infinity, x squared over something, plus 3x over something, over 5 over something, minus x over something. And that something, again, is going to be your what? X. Okay. So we get now the limit as x goes to minus infinity, x plus 3 over 5 over x minus 1. Is that true? Okay. Now again, by properties of limits here, right? We're going to use our properties here. What this becomes here now is really by properties. Maybe we should write that down just to remind people, right? You're going to use your properties of limits. So by all those properties, without going through all that detail like we once did, this is going to be the limit here of just the x plus the limit of a constant 3 over 5 times the limit of 1 over x. X goes to minus infinity, minus the limit of our constant 1. Okay, now let's evaluate every one of these limits here. So what do you guys know? What's the limit of x as x goes to minus infinity? This is going to be what? It's negative infinity, is that right? What's the limit of your constant? Yeah, limit of the constant is the what? Constant. Okay. And this is another constant, so that's going to be 1. And what's the limit of 1 over x?
0.
That's 0. So altogether now, we have negative infinity plus 3 over 5 times 0 minus 1. Is that true? Now we're going to go through what we just discussed here about what all this really means again, right? And so for your numerator, if you guys notice, yeah, right up here in the numerator, you got negative infinity plus 3. So what's that going to give you? That's negative infinity. Good. And then 5 times 0 minus 1, what's that going to be? It's negative 1. Is that true? And then now you have negative infinity divided by negative 1. What does that equal? Is that negative or positive infinity? Positive infinity. Good. So let's remind you guys that this is not a what? This is not a horizontal asymptote at all. Okay, this is describing your end behavior, and the end behavior that it's describing is simply as x goes to negative infinity, right? Your y coordinate value goes to what? Positive infinity. Okay, so you're looking as x goes to the left. So that means y is getting big without bound. So you have two situations that it can look like, right? It could look like this, or it can look like what? That. Let me get this a little better. Yeah. It could be concave up or concave what? down for this end behavior. So this is what we're looking at. As x gets big, as x goes to minus infinity, which is a form of small or a version of small, because the further to the left you go, the smaller the number, y is getting big. So this is either a concave up situation or a concave down situation, okay? It is not horizontal. So we want to make sure you guys know this. This is not a horizontal asymptote at all. Okay, good. Situation number 3 now, or question 3. We have the limit here as x goes to infinity, now of cosine 1 over x squared. Okay, so this is going to be an example to share with you that when you go to the Calculus 2 course, right, the second course, you're going to see a lot more questions that look like this. And this is actually based on what's called composition of functions, right? You have what's called an inside function here, right here. The inside function is 1 over x squared. Okay, so what can happen now for us, or a way to do this, is to introduce a variable here for this. You're going to let now t be 1 over x squared. Okay, so that the limit question now is going to become the limit as x goes to infinity now of cosine of t. Okay, all I did was substitute here for what t is, right? We say t is going to be 1 over x squared. And so here's going to be what we really have to think about now. Okay, you see this is a limit as x gets big now. And your variable over here is not x, it's now t. So we have to understand what's happening here. Here's what I mean. As x gets big, what happens with the variable t, since what do we know about t now? See this here? Yeah, t is 1 over x squared. So we have to see what happens to t, since it's 1 over x squared, as x gets big here. So go back up here and say, okay, right? What does t approach? Since your x coordinate value down here is getting big, right? What do you guys think is happening with that t?
0.
That's going to 0. That's right. And you say, well, why is that going to 0? Because again, if you go back to the curve, right? This is now a function here where you have still 1 over x squared. Here's the x coordinate. Here's your t coordinate. Okay, so as x gets big, over here, all your values again, all the points in the curve, the y coordinate values are going to 0. So you're right. So that's going to be a 0 here. Okay, so this means t goes to what? 0. So your question becomes, what's the limit as t goes to 0, cosine of t now? And you know something special about cosine. What's so special about cosine? Cosine's a continuous function, right? It's continuous everywhere. So why is that a big deal for cosine to be continuous? Okay, well, let's write that down. Cosine of t is continuous for all real numbers. Why is that important again? Because we can evaluate the limit by just doing what? Putting 0 in for t, also known as direct substitution. So do you guys know what's cosine of 0? That's 1. So what this means here, in conclusion here, that this limit here really equals 1, and that means y equals 1 is a horizontal what? Asymptote. Okay. Let's see if we can figure this out here for the next question that we have here, which is the limit now as x goes to minus infinity, sine of, is that 1 over x cubed? Okay, you guys okay with that one? Okay. So again, this is just like the last problem, where you're going to introduce here a substitution here, right? See this right here? We're going to substitute because this is a function in another function. This is really composition of functions. So we're just going to call this t. So we're going to let t equal 1 over x cubed. And so again, this becomes a limit still as x goes to minus infinity, sine now of t here, but you still have the issue here of a limit question in terms of the variable x, and you have a function in terms of the variable t. So we have to consider again, as x goes to minus infinity, since t is 1 over x cubed, where does that actually go to? Do you guys know where that one goes to? Right? What you got 1 over x cubed right in here. What happens as x goes to minus infinity? What would you say that goes to? Goes to 0. Good. So this is going to be now as t goes to 0. So you really have the limit now for t going to 0, sine t. Now, what's so nice about sine? Sine is what? Continuous everywhere. It's a nice continuous function, and that means that sine of 0, we can just plug in the 0 for the value for t, right? Direct substitution, and you guys know what sine is 0. That's 0. Good. So this is going to be here now. Go back. Equal to 0. Now remember, because this is finite, what does that actually mean? Yeah. We say y is 0 is a what? Horizontal asymptote. That's our conclusion. Okay, you guys okay with that? And then maybe just to kind of take a look here, I'm going to try to do something here. Let's try this out. This is sine of 1 over x cubed, right? Sorry. Let's get rid of this curve. How do we get rid of this? Yeah, there's a little glitch here on this. I was going to show you something very, very interesting. Should get rid of this. It's okay. We'll actually show you in another demonstration what we're looking at. Hopefully, yeah. Yeah, let's get rid of that if we can figure out how to get rid of this. Guess they want us to do some what? Yeah, it's going to have to be restarted, I guess. But anyway, I wanted to show you guys the graph here of this. Let's just say add to photos. And yeah, it looks like the app isn't working on this right now. So whatever. Yeah, there you go. Life with technology. Okay, let's go back to our questions here. Number 5. This is the limit as x goes to infinity now. We have what? X squared plus 2 over x cubed plus x squared minus 4. Okay? Double check to see if I'm writing this down correctly. So again, what are we going to do here? Divide every term by what? By x cubed. Is that right? Okay. So we can get the limit now. X goes to infinity. X squared by, divided by 2 divided by x cubed over x squared over minus 4 over. It's going to be that x cubed. Okay, let's do some algebra now. Limit x goes to infinity. This is 1 over x, right? Plus 2 over my x cubed over 1 plus 1 over x minus 4 over what? X cubed. Properties of limits, right? I won't write down, I'm just going to say here, use properties again. Okay. Limit x goes to infinity of 1 over x plus 2, limit 1 over x cubed, x goes to infinity, over limit of 1 plus that limit of 1 over x minus 4, limit 1 over x cubed. All by properties. Okay, let's see what happens here. Let's actually make it look a little nicer here. Right. Okay. What's this limit going to be? 0. What's that limit? 0. What's this limit? 1. Limit 0. And then 0. So we get 0 plus 2 times 0 over 1 plus 0 minus 4 times 0. So if we do the arithmetic, this is 0 over 1, which is going to be what? 0. So what we know now is that what? Y equals 0, since this is finite, is a horizontal what? Asymptote. Okay, and that's because, again, that this is what? Finite. If this was infinite, then it would not be a horizontal asymptote because it wouldn't be horizontal. Is that right? Okay. All right, number 6. Number 6 is going to be interesting here. This is the limit. X goes to infinity. What is that? X plus 2. Yeah, we got x plus 2 over square root of what? 9x squared plus 1. Okay. So yeah, this is going to be a very interesting kind of thing here. Okay, because if you said to me, if I said to you guys, what have we been doing here? We've been dividing by the what? By the variable with the highest power in our denominator. Is that right? And what do you guys notice though in this case? You got a what? A square root in that denominator, don't you? And you got the square root of 9x squared plus 1 here. So even though your denominator here is not a polynomial because of the square root, right? You got the square root of a polynomial. So we have to think a little bit on this one, and we're going to have to still go with the same premise here. And I want you guys to understand one thing here. The square root of 9, or I should say the square root of even x squared, it doesn't really matter what the number is. What you're going to do here is go with the idea that you have here the square root of what? X squared here. It's in your denominator. So if we look at the square root with the variable, we can ignore the constant. We can now kind of figure out what the variable with the highest power would be. Is that right? So we have the square root of x squared, and what does that mean? Do you guys know? Yeah, the square root of x squared, you can say, is the value x. However, let's go back to pre-calculus here. right? The square root of x squared is not exactly x. Is that true? Let's see. Let's go back here. Let's write it here. The square root of x squared is actually two things. It's x when x is greater than or equal to 0, right? And it's minus x when x is what? Less than 0. Because this is actually the absolute value of x by definition, okay? So if you guys remember, we can also think of this as the what? Absolute value. Let's go here. Let's write it. Absolute value of x or square root of x squared. So here's where our issue is going to be here. Now, remember what I said to go back and look at this what? Look at that limit. X is getting big. So what does that mean for this function? That means my x value is what? Positive. And that should make sense. Is that true? Now, x can be negative, but you're squaring it here. It's making it positive, but up here it'll be a negative value. So it's still going to be defined when x is negative. Okay? But the limit question applies to x being positive. So here's what we're going to get to use now. Since my x value here is positive now, when I say to you, divide every term now, what are we going to divide every term by? Let's make sure this goes back on so you guys can see. There you guys go. Okay, so here's what's going to happen with this. You're going to have the limit still, x going to infinity now. We're going to divide every term here. Every term gets divided by what? By x. So there's going to be an x down here. There's going to be an x down here because this is, in some sense, the variable with the highest power in the denominator. Is that right? But you have a radical, and you have 9x squared here. Plus 1, and we're going to still divide that denominator like before with that x variable. Okay, you guys okay with that? But the issue here is I can't get under my radical, can I? Since this down here, right, this is my x value. What do I know about x, though? It's going to equal the square root of x squared. So since x equals that square root of x squared, I can replace this with square root of what? And now I could get under my radical. So what you'll see now is this limit now as x gets big here. 1 plus 2 over x over, well, what happens when you have a square root? You guys see this here? Square root of 9x squared plus 1 over square root of x squared now. What's the square root over a square root? I can put them under a single radical, right? Square root. 9x squared plus 1 over that x squared. Okay, by properties of square roots, or properties of radicals. What happens now is we have the limit as x gets big, 1 plus 2 over x over square root now, 9x squared over x squared plus that 1 over x squared. So the same kind of algebra is going to take place here. You got the limit, x goes to infinity, 1 plus 2 over x over the square root now of 9 plus what? 1 over x squared. And as you guys can see now, we're going to write this down again. You're going to use some what? Use properties of our limits. So by properties of limits now, this is going to equal the limit of a constant plus 2 times the limit of 2 over x. And this is again as x gets big. Over, remember you have a limit of the square root. What can we say? Square root of the what? Of the limit. Is that right? So this is the square root of the limit of 9 plus that limit of what? 1 over x squared. And this is all by properties of our limits. Okay. What's the limit of a constant? The constant, oops, and this should be, we pulled out the 2, right? What's this limit here of, right? We're going to find that limit here. What's that limit? That's 0? What's this limit? 9. What's this limit? 0? Okay, you guys okay with that? So if we put this together, we notice that this is 1 now plus 2 times 0 over square root of 9 plus 0. And doing our arithmetic, we end up getting 1 over the square root of 9, which is going to be 1 what? 1/3. So what we can say now here is that, let's put it here, y equals 3, since 3 is finite, is a what? It's a horizontal tangent. 1/3, sorry, let's go back there, 1/3. Still thinking about that app that doesn't work. So it's a really good app though. I like that app for graphing. Asymptote, yes, thank you. See how I get distracted when something works? Horizontal asymptote, not tangent. Sorry. Y equals 3. It's a vertical line. Anyway, that's a good question. We're going to actually take a look at another example here where you go to minus infinity, and you're going to see that there's a slight difference here. Okay, maybe we should consider that now. Maybe we should make that a note. Let's try to think of that as a note here, right? So let's note something here. If they said, what's the limit as x goes to minus infinity now? And that same question, we'll look at it that way, yeah. We'll have what? X plus 2 over square root now, 9x squared plus 1. Remember, what was the key here? The fact that you're taking the square root, right? You're taking the square root of x squared. You don't really have technically a rational function. You don't have a polynomial in the denominator. But we still use the same approach. We divide every term by the what? By the highest power, the variable, in your denominator. And then you say, okay, well, what does that mean for us? Well, that means I have the square root of x squared here, which can be thought of as the absolute value, which is defined piecewise. Okay, and in this case, since it's in the denominator, so you guys know, x is not going to be 0. Well, yes, it can be. Sorry, I take that back. Okay, so remember this. This is where we're at now. So we already looked at that concern. We're going to have to divide every term by what? Yeah, what do we divide every term by? Yeah. Okay, so we're going to have to divide every term by that x here. And we go back and you say, let's write it all over. Have x plus 2 over square root 9x squared plus 1. You say, okay, I'm going to divide every term by x. Okay, so far so good? Well, we're going to see. I'm going to tell you guys that x certainly can be negative, can it? You see this limit? X is negative, and x could be negative. Is that true? Okay, however, I'm going to say to you guys, here's what you guys want to do. Do your algebra here. you still have that limit of x going to negative infinity. We still have 1 plus 2 over x. We're still going to apply the x approaching negative infinity here. I know x is negative. But if you're going to try to get under the radical here, remember this? You got 9x squared plus 1, and you're trying to get under that radical, and you can't because you have what here? X. Is that right? Here's what you guys get to use. At this point, use the fact that the square root of x squared is going to be minus x because x is going to be negative here. So you're going to try to get under that radical. What the algebra says now for this would be simply that what? X is minus square root of what? X squared. So you're going to put a negative square root of x squared down here so you can get under your radical. So you get now the limit still, x going to minus infinity, 1 plus 2 over x, and now this is going to be over minus square root 9x squared plus 1, everything over that x squared, right? Is that right? So you just pulled out the what? That minus sign that's here. And you leave it there. And again, square root of your quotient is quotient of square roots. So you get now my limit as x goes to minus infinity, 1 plus 2 over x. I'm going to put the negative sign here. Square root again now. Yes, it'll be 9x squared over x squared plus 1 over x squared. You get that limit here. X goes to minus infinity, negative 1 plus 2 over x, square root of 9 plus 1 over x squared. And again, by your properties of limits, if you guys recall, you know, this is going to go to 0, right? And this is simply going to go to what? The square root of 9. So that your final answer is going to be negative 1 plus what? 0 over the square root of 9, or negative 1 over 3 here. So what this means is, as x goes to negative infinity, my end behavior is different. It goes to a negative 1/3. So at this point here, we have another horizontal tangent here. That's the line being negative 1/3, horizontal asymptote. And this applies as x goes to negative infinity now. So you have two different approaches for this function. As you go to the right, x goes to positive infinity. Your horizontal asymptote is 1/3. As you go to the left, it's negative 1/3. But that's what you're going to have to use for this kind of question here when you have that square root. So I just wanted to give you guys that note. Okay, good. And now we have another example here. Okay, so we're going to change the order. Like I said, this is going to be number 7 here. We're going to find that limit as x goes to infinity for this polynomial function. Okay, and so if you remember how we start this off, right? We're going to look at this as the limit of a sum here. So you have the limit as x goes to infinity, x cubed, plus the limit x goes to infinity of x squared here. Okay, and so what do you guys remember about this? Right, this first limit here, x is getting big, and if you raise that to the 3rd power, what do you think happens with the x cubed term? That's also going to be what? That's also going to be big, is that right? I'm going to say plus here. Let's do the next one. And we know, again, x is getting big, so what do you think's happening with x now as it gets big, and you're raising that to the 2nd power now? Well, that's getting even bigger, is that right? It's getting bigger faster. So in both of these cases, you're getting big. In the first case, you're getting big really to the third power. In the second case, you're getting big to the second power. So if you guys recall, what does this mean if we add these two? Right? These are ideas again. This isn't finite sort of arithmetic, right? These are not finite numbers. This is a concept. So if you guys recall, we kind of think of it this way as what you do what with this? You have Oprah money plus Bill Gates money. What are you going to end up with? Yeah, a whole lot of money. Okay, so here's going to be our new number 7. I modified the questions for a different order for a good reason. And then I'm going to say here, let's give you guys a note, or by the way, let's put this as a note here. What if this question was the limit as x goes to minus infinity of x cubed plus x squared here? Okay, we're going to change this limit here. It's a different question because now you're going to minus infinity. Okay, so now you're going in the other direction. And again, by properties, you have the limit of a sum becomes sum of limits. So this is my x cubed plus that limit. X goes to minus infinity of x squared here. Right? So as we focus on these limits again, this is going to go to negative infinity now for both of these here. Okay, and going to negative infinity, by the way, is a version of going small. You're going further to the left. The further to the left you go, the smaller the number is, right? So I want you guys to understand that you're going to the left now. Now, again, the question is going to be, what happens to the x cubed term as x goes to negative infinity? Well, yeah, it's because you're cubing, it's still going to be negative. Is that right? Yeah. And so you're going to go to negative infinity here for the first one. And we still have our addition. That'll be infinity. And the next one, yeah, because the power here is 2. And so as x goes to negative infinity, we square that, right? And what happens? It's going to be positive. So you have negative infinity plus infinity. Okay, now remember what we said last time here. This is going to be an indeterminate form. We can't determine. Okay, we cannot determine what that is. It's not finite arithmetic. It's not finite numbers here where you have a negative 5 plus a 5, right? So we wrote this down last time, and we know that infinity minus infinity was indeterminate. And this is actually the same thing. And so the question here is, what do you do in this situation when you can't determine, right? Well, I'll tell you what we always do. We use some what? We use some algebra here. So this is kind of the stuff we talked about last time, right? So if we have to use algebra now, this question here, what kind of algebra did we do for this example in the past? You guys remember? You factored, is that right? So when you factored here, let's write that down. You're going to factor, and you're going to factor out the greatest common factor. So this will be x squared plus x times 1 here. So here's your new limit question. And again, by properties of limits, the limit of a product is really a product of limits. So I have the limit, x goes to minus infinity of x squared times the limit, x goes to minus infinity of x plus 1 here. Right? So you're going to go now again to minus infinity for both of these. And so for the first limit, again, you can recall that we're going to square that x. So this limit's going to be, again, positive infinity. And this limit, anybody remember, what's this limit going to be? Right? X goes to negative infinity. Is that right? So negative infinity plus 1 here. What does that mean? If you owe Oprah money, but you add $1, right? What do you think? Do you still owe? Yeah, you still owe, and you owe a lot of money, and so we just designate that as negative infinity. Okay, so we can actually determine this. This is a positive idea times a negative, which will give you a negative, and that's going to be negative infinity. So I want to point out to you that if it's indeterminate, like we had here, right? This indeterminate form, we're just going to use some algebra here. Okay, and that's kind of the idea. All right, so we wrote all this stuff down last time. We talked about it. And I'm going to go with this in a different order. So I want to remind you guys that can happen. And number 8, we have, what do we have? We have the limit as x goes to infinity. You have x minus the square root of x. Again, by properties of limits, the limit of a difference will be difference of limits. Well, let's kind of back up really quick here, right? Since this limit is going to infinity, right? By properties, we know we just have to take the limit of x minus that limit of square root of x, and this is as x goes to minus infinity, right? X goes to minus infinity. And so, since x is going to minus infinity, what do you think happens with this first x? Right? This is just minus infinity. That's the same x. Now this is minus, and then you say, oh, I apologize. Let's go back. That's not minus infinity. That's a positive infinity. Okay. Now that makes a lot of sense. Okay, apologize for that. See this? This is going to positive infinity. Okay. If you change one of these signs, then you change the whole essence of the question. So, all right. As x gets big, arbitrarily big, goes to infinity, this is the same x. So this is arbitrarily big. That's infinity. Okay. Minus now, what happens over here to the next function? This is the square root of x. So as x is getting big, what's happening to the square root of x? That's also getting what? Big. Okay? So we have this getting big minus getting big. This again is indeterminate. So we know we can't determine, and if we can't determine again, what do we have to do? Use some algebra, yes. Yes, you're going to factor that. Okay, now, again, this is a situation where you may realize and you say, wait a minute, how am I going to factor this x minus square root of x up here, right? This is what we're going to have to factor. And you're going to factor out the greatest common factor. So you have the limit here, x gets big, x minus the square root of x, and you're going to have to factor. So what we mean factoring, you factor out the greatest common factor, right? And so if you guys recall, this is a 1/2 power. What's the greatest common factor of this difference, right? The greatest common factor for variables is always going to be, remember this GCF? It's going to be x to the what? The smallest power. Okay, so we're going to factor this here. I'm going to go through the details. We're going to write this term here, this difference, as a greatest common factor times a quotient. Okay, because I know that this is probably something people need to really review and think about, right? So if you factor out a greatest common factor, in this case, the GCF is going to be x to the what? 1/2. Is that true? Now you say, why is it x to the 1/2? Because the powers here, this is a 1 power, this is a 1/2 on the other side. So 1 and 1/2, the smallest power is going to be 1/2. Is that right? So then the question becomes now, how do we find this quotient here? Right? You see this term here, how do we find that? Now in the past, we reminded you that just take the original expression, x minus x to the 1/2 power, that square root. And you always divide by that GCF. You divide by the x to the 1/2. this is going to give us the quotient, because the quotient means to divide. It's the term you get when you divide. That's called the quotient. So now by properties here, or I should say we distribute our division, right? So this is a technique that's going to come in very handy with us. That this quotient here now is going to be, this is the first power. So by beginning algebra, this is our intermediate. This is x to the 1 minus 1/2 minus, this is just 1. And so I get x to the, this is 2 halves minus 1/2, or simply x to the 1/2 now, minus 1. So my quotient's going to be the square root of x minus 1. So that goes right up in here. Okay, this is the quotient that we just found. Altogether, your limit looks like this. This will be x to the 1/2 square root of x to the 1/2 minus 1 here. And that's how you factor it. So our limit question is going to be the square root of x times the square root of x minus 1 here. So now you can actually find your answer. You could determine this because the limit of a product is product of limits. So we get the limit as x goes to infinity, square root of x times the limit x goes to infinity, square root of x minus 1. And so this first limit is going to be what? What's the first limit going to be? Infinity. What's getting big again? X is getting big, is that right? So as x gets big, the square root of x gets big as well. Maybe slower, not as fast, because it's the square root, is that right? But it's still getting big because x approaches infinity. And for the next answer here, you say, okay, x is getting big. What's going on for the next one? Well, the square root of x, it's still getting big. Same x, right? So something getting big now, minus 1. So if you had Oprah money minus 1 here, this is what you're thinking of. Oprah money minus 1, right? What do you think you're going to have still? Oprah money. It's not going to make a difference. Is that right? So this is infinity times infinity, and that's how we think about this. So this is going to be, as a final answer, what? Infinity. Now, I want to remind you guys a few things about what this means, okay? Let's go back. Even though this is limits at infinity here, and the final answer here would be infinity, we want to think about what this means. This is in the context of a pre-calculus course, right? This means really the end behavior of the function as x gets arbitrarily large. Okay, x goes to infinity. You may notice something about this function, this curve. What do you guys notice? If you look at the domain, the values of x have to be what? Greater than or equal to 0. So let's try this out. Let's hope this app works today. This is x minus the square root of x. I want to kind of remind you guys, you're looking at the end behavior as x gets big. And let's try this out. This is kind of my favorite app for graphing. So we have y equals, what was the function again? X minus the square root of x. Is that right? Yeah. And let's find our functions. Oh, I don't see our functions there. Do you guys see a square root? Oh, here we go. It's over here. Square root of what? X. So sure enough, as x gets big, what's going on with that y coordinate value? It's going to infinity. And notice this, is the function defined for negative numbers? The answer is no, right? You cannot have negative x values, so that kind of makes some sense. So we're looking at end behavior again, and to really summarize this, here's what you guys will see hopefully in Calculus 2, right? We're saying as x gets big here, y is getting what? Big as well. All right, that's kind of the summary of what you want to think about. As x gets big, the y value is getting big as well. That's what the limit question is happening here. The prior example, you may say to me, okay, Mr. Judge, we say that limit was negative infinity here, right? So because this limit's negative infinity, let me remind you guys, what's the domain of this function here? Your domain is going to be all real numbers. Good. Right? So this is defined for every real value. So what this means here is as x gets big, goes to infinity, y actually goes to minus infinity here. Okay? That's the meaning, the physical meaning behind what you guys are saying. Now this curve is x cubed plus x squared. So let's see if we can take a look at that one. Okay? So we'll have y equals x raised to the third power now. And that was plus x raised to the second power. And so as you guys can see, what was that limit question, by the way? X is going to negative infinity, right? Or what was that? X going to positive infinity? What was that? I guess it's still on the board. As x gets big, what happens to your y value? Look at quadrant 1. Y is getting what? Big. You see this here? And notice the other side. What's going on over here? It's doing the opposite. As x gets small, meaning going to negative infinity kind of small, y is going to negative infinity. Is that true? So this is describing end behavior, and maybe we want to take a look at that one. And, oh, we did. Take a look. This is negative infinity. So, good. This equals negative infinity. Oh, I apologize. We looked at the wrong one. Got to drink some more coffee here. Here we go. This was equal to what? Negative infinity. Okay. So this was as x goes to what? Negative infinity. Y goes to negative infinity. Good job. And this one, though, is actually not negative infinity. It's what? Positive infinity. So let's change that here. Good. So we actually looked at the note answer. All right. Okay, so this now makes a lot of sense, right? As x gets big, y gets what? Big. As x gets small, y gets small, meaning going to negative infinity. So the graph does verify this. Okay, you guys okay with that? That's the polynomial we're looking at. So we're looking at the end behavior of these things by looking at these limits. So I want to remind you guys that. Pretty good. And now that leaves us to what? It's going to leave us to number what? I guess that's 9, right? All right, let's look at number 9 here. Okay, 9 is interesting. We have the limit as x goes to what? Infinity. 2 plus x cubed. 1 minus x. And then 3 minus x. Okay, we're going to do this limit question now. So again, the limit of a product is product of what? Product of limits. So when I actually see this, this is what I do in my mind. I'll write the details for us here. And as you guys can see here, x is getting what? Big. Okay, that's the question. So what happens here now is, let's think about this. This is the same x. That's pretty big, is that right? So if I have $2, here's my $2 plus my Oprah money, I got a lot of money, is that right? And then guess what? I get to cube my money. So what does that mean? I got a lot of money. That's pretty big. So as x gets big, this term gets big faster. Right, that first term. Now, what about this here? What's happening with the next one? As x gets big, I got 1 minus big, that's thinking of this as how? 1, and you owe now Oprah money. So if you owe Oprah money, but you have $1, I got some bad news for you. You still owe an arbitrarily large, or in this case, small amount of money, right? So there you go. And then what about this over here? 3 minus infinity. This is a limit. So 3 minus infinity now, that's still going to be what? Negative infinity. So if I have a negative times a negative, I get a positive. So this is really infinity times infinity times infinity. What do you think that means? We're just getting what? Big. Okay, and so what that means is, as x, since these are really limits, okay, these are approaching infinity. They're not finite values, even though we kind of thought of it that way, right? As x gets big, we know y is also getting what? Big. Okay. So let's kind of think about this one here. In terms of end behavior, so you guys know. Since all of this is really about finding this end behavior, if we note the following here, and we look at the limit as x goes to minus infinity, 2 plus x cubed times 1 minus x, and 3 minus x. All right, you guys okay with that? What you kind of can do is, you know, if you know this is the limit of a product and product of limits, what I kind of do just by looking at this, I know, okay, this is negative infinity, right? So 2 plus a negative infinity is actually going to be still negative infinity in a way, right? And if you cube that, what do you get? Minus infinity. What about over here, though? Minus and minus makes that a nice plus. Is that right? So this is going to be positive infinity, because this becomes, like, in some sense, 1 plus infinity, although this doesn't make sense because these are limits, but we can look at it that way. This is 1 plus Oprah money is still going to be Oprah money. And then I got 3 here, right? Minus a minus infinity. That's still plus. Just like over here, we put that minus infinity. $3 plus Oprah money is still going to be some pretty big money. Is that right? And so if I have, since we can find the product here, this is minus infinity in a sense, approaches negative infinity, approaches positive. By the product rule, this is minus what? Infinity, because you have one negative sign and the rest are positive. So in summary here, we can say as x goes to minus infinity, y goes to what? Minus infinity as well. So we're looking at the end behavior. So for some of these polynomials, we could deduce the answer pretty quick mentally just by thinking of this idea, okay? So I want to point that out again. Again, this is about end behavior, and let's take a look. Let's see if we're correct here. So we're going to put here y equals, oh, what was that first term? 2, it was 2 plus x? Yeah. And then I got to come out here, got to go to the power position, and that's going to be a 3. All right, that's just going to be 2 plus x cubed, ladies and gentlemen. Notice the end behavior here. You can use those limits at infinity and minus infinity to look at end behavior. But that's not what we have. We also have what? What was that? 1 minus x? So this is times 1 minus x. Okay, it's getting a little bit more complicated. Got to come out of that parentheses with another parentheses. And was that 2 minus x?
3
Oh, 3 minus x. 3 minus x. And here we go. Now let's see what this curve looks like. I don't know if you could see some of this. Yeah. Could be even the software. But I want to kind of point out to you, you see this left side here? As x goes to negative infinity, this is going down to what? Negative infinity. And then the right side here, as x gets big, what's going on here? It should be going to positive infinity, but did we write this in incorrectly, you think? Let's see where this is going. This could be an error here with this software. Looks like it's an asymptote, but that's not really an asymptote. Sorry we even did that. So let's double check. Is that our right curve? Yeah. Anyway, we'll probably have to look at another software program that can graph a little better. Anyway, that's the idea. You're looking at end behavior. Okay? And then finally, let's do the granddaddy question. Now that you guys have some experience here with these limits. Okay? We're going to look now at the next one. The limit here, as x goes to minus infinity, we have x plus square root x squared plus 2x. So this is a good exercise, and this is the one reason why I wanted to rearrange the order so that you guys had some experience with these limits at infinity. Now, if you notice again, in this case, what are we doing? We're approaching negative infinity, is that right? So this first term that you guys see here, yeah, that's going to mean you have negative infinity now, plus, now let's do the radical. Under your radical, x goes to negative infinity, we're going to square that same x. So that means it's pretty big, is that right? So under radical, I got infinity. And then what do I have over here? Yeah, anybody see anything here with this one? Let's double check. Let's make sure we wrote it down right again. Yeah, I think this is a correct one. Anyway. So under the radical, I have a problem already because what's the deal here? Is that minus infinity? So this is indeterminate here. So in this portion here, this is indeterminate. Anyway, okay. So I already know that this is indeterminate, and indeterminate means I can't determine. So then the question is, what do you do here? Well, the answer is we use what? Algebra. Now, let's double check. Yeah, that's the exact question. We use algebra. But I want to remark here. I'm going to say, by the way, really, really quick, let's note that if they gave us the limit as x goes to positive infinity of the same question, what do you guys see happening here? See that limit's getting big? Well, this x is getting big. This is the same x. Plus, what's under the radical now? Under the radical, x squared, that limit is infinity. 2x, the limit is also what? Infinity. So under my radical here, I'm taking the square root of something that's getting big, and that's going to be big as well. So I got big plus big. This limit is going to be infinity here. All right, so we knew that from the other day. So this is not the question we had, so I want to double check. So, okay, let's deal with reality. The reality is that x is going to actually negative infinity, and so we're going to have to use some algebra. Now, the algebra that you guys want to use here, okay, this is going to be, we're going to say you're going to use what's called the conjugate. And it's technically the irrational conjugate. All right? It's the irrational version because you have an irrational. So let's look at this way here. I'm going to change that to blue maybe. So I have x plus the square root of x squared plus 2x. We're going to multiply the top and the bottom by the irrational conjugate. So that's x minus square root x squared plus 2x. x minus square root x squared plus 2x here. So you're going to do this whenever you have an indeterminate form that involves that sum or difference where you have a radical here. See this? And those pop up every now and then. Your book has a good example, but I don't want to do the example from the book. And so what you do now, if you recall, is you're going to just multiply here as if you were multiplying fractions. And so my numerator, be very careful here, right? Because this is irrational conjugates. So by FOIL, the O and I terms go away. Okay, so you're going to use FOIL here. This is the algebra portion. And O and I terms disappear. So this is what that means. My first terms are still there, so I have x squared. O and I terms gone. My last term is there, so I multiply these two terms together. And that's going to be minus now. Now remember, what happens whenever you multiply radicals? And in fact, you got the same exact terms under these radicals, under these square roots. Remember this? Yeah, doesn't just the radical go away? So algebraically speaking, the radical goes away. This is a lot easier to deal with now. And that's my numerator divided by still x minus the square root of x squared plus what? 2x. Now, when I distribute, right? So let's distribute here. We simplify this. You're going to get now, as a numerator, x squared minus 2x, everything over this x minus what? X squared plus what? 2x. And so you end up now with this negative 2x over x minus square root x squared plus 2x. Okay? And we're supposed to take the limit here as x goes to negative infinity. Now, as I start to look at this again visually and see what happens at negative infinity here, right? Because we're going to go to now negative infinity with this. The numerator portion here is going to be, this is positive infinity, right? Because a negative times a negative is a positive. And the bottom here is going to be a negative infinity minus, and then you have that square root, and you're going to have that again, infinity minus infinity again. This is also indeterminate, is that right? So we have indeterminate. So how is it that I'm going to actually handle this if it's indeterminate again? Right? You're going to have to, let's go back and think about this here. What did we do yesterday with some of these examples when you had rational functions? Do you guys remember? What do we do? We always, with rational functions, you have a polynomial in the numerator, polynomial in the denominator. You always do what? Divide by the variable with the highest power in your denominator. Is that right? And so if you look at the denominator now, because this is indeterminate, meaning we can't determine. We're going to divide by the variable in the the highest power in the denominator. You have an x here, and what else do you have? See this radical again? What did we do yesterday? Right? See this right in here? Square root of what? The x squared. What's the square root of x squared? Isn't that x? So I want you guys to note here that we're going to divide every term by what? By x. Because the square root of x squared is going to be that x value that we have right in here. Is that right? The square root of that x is that's x to the 1/2 power, so that's not the highest power. Is that right? So that's how we look at it. And now this is actually just like what we did yesterday. And let me do this again here. Let me remind you guys here. So let's be careful here. We got minus 2x, x minus square root x squared plus 2x. Okay, what are we going to divide by again? Every term is going to be by that x, by this x, by this x. Is that right? And what you end up now with would be negative 2 in the numerator, 1 minus square root of x squared plus 2x. This is over x. And if you guys remember again, you have an issue here. What's the issue going to be? I have to get under the radical, don't I? Don't I have to get under that radical right in here? Let's change this color here. This is what we're focusing on. We got to get in under that radical, and we can't. What do we have to do again? We're going to have to go back and think about this again. What do we have to use? I know we wrote down here the square root of x is x, but that's actually not completely true in this case. Is that right? Anybody know why that's not true? Because x is going where? X is going to negative infinity, so x is actually negative. Is that right? So this is kind of a, sorry. Guess the school wants us to. What does the school want us to do? There we go. All right, let's see if we're still rolling. Yeah, we're still rolling. Okay. So I want to go back and remind you guys that, this statement is not completely true here because x is actually negative. Is that right? So since x is actually negative, let's get rid of this. This is what we mean. We can still divide by x. It got us that far. What do we use here? Do you guys remember? Let's write down what this really is. Yeah, remember we said the square root of x squared is in fact x, but that's true when x is greater than or equal to 0. Is that right? This is piecewise. It's opposite x when x is actually what? Less than 0. Okay, because this is really the absolute value of x. So we define this piecewise. Now, how this is used here is we can say, well, at this point for my radical, really, okay, since x is what again? Negative. X is negative. What you're going to use here, in this case, is that relationship. You're going to use the fact that the square root of x squared, which is that x, is actually minus x. Or we can say that x in this case gets replaced with minus square root of x squared. So here is what we actually use now for that x down there. Okay? So we're going to replace this x now here with minus square root of x squared, because we just solved for that, solved for the variable x here. So we divided by -1, and this is what we get. That's going to help us here. So what we end up with here, ladies and gentlemen, is -2 over 1 minus, now that's the square root of x squared plus 2x. Yes, we divide by this negative square root of x squared. So algebraically, we get what? -2 over 1 plus square root of what? X squared plus 2x. And I'm going to have to, let's put this under a big radical because that's what's happening here. Okay, these two signs right here and here, negative and negative, makes that now a positive. And the square root of a quotient is quotient of square roots. I can now proceed with my algebra here. All right, this is where we're going to work with. So this is -2 over 1 plus the square root now of x squared over x squared plus 2x over x squared. And what do you end up getting, ladies and gentlemen? This is -2 over what? 1 plus the square root of 1. What's this? Plus 2 over x. Good. And if you like, you can put the negative sign right up here. Now, don't forget, this is all about taking a what again? limit as x goes to negative infinity. All right, so now the properties of your limits. Limit of a quotient is quotient of limits. Limit of a sum is sum of limits. Limit of the square root, right? You remember all those properties? So now we're going to use properties of limits. Now let's say, make sure we write this down. Use properties of limits. Here's what you end up with. This is going to be negative 2 over 1 plus the square root of 1 plus 2 times that limit. X goes to negative infinity, 1 over x. So let's make sure we have this a little nicer. All right, you guys okay with that one? Does that look okay to you guys? That was the stuff we worked on the other day, is that right? And then what else did we learn the other day about this limit right here? What does this limit go to? That goes to 0. So using our arithmetic now, we have negative 2 over 1 plus the square root of 1 plus 2 times 0. And that'll be negative 2 over 1 plus the square root of 1. Is that right? Is that true? And that's negative 2 over what? Is that 2? Is that true? You guys okay with that one? What's this going to give you? Is that negative 1? So my limit here is negative 1. Let's double check. So in conclusion, you say, well, what does this mean? Right? This means this. As x goes to negative infinity, y goes to what? Negative 1. What does that actually mean? Do you guys know? Anybody know what this means? Let's write that down again. What's the whole idea behind these limits? Yeah. So what does this mean? It means this is a horizontal what? Asymptote. And where's that horizontal asymptote at? Y equals negative 1. Or we should say that's the equation that describes our horizontal asymptote.